This is Inorganic Chemistry. Chapter 1, Atomic Structure. Section 1.1, Spectroscopic Information. In a hydrogen atom, there's only one proton and one electron. The energy of the atomic orbital occupied by the electron is -1 over 2n squared. The unit is atomic unit of energy. N is the principal quantum number. One atomic unit of energy is 4.36 attojoule, or 4.36 times 10 to the power of -18 joule. So the energy of the 1s orbital is -1/2 atomic unit. The energy of 4s, 4p, 4d, and 4f orbitals is -1 over 32. What about 5s, 5p, 5d? -1 over 50. 6g, 1 over 72 atomic unit of energy. And these numbers are for the electron in the hydrogen atom. For helium plus, or lithium 2 plus, or beryllium 3 plus, or boron 4 plus, there's also only one electron. And it's possible to calculate the energy of the electron, which is also the energy of the atomic orbital occupied by the electron. It's -z squared over 2n squared. Over here, you have this nuclear charge squared on top. So for helium plus, this is 4, 2 to the power 2. For lithium 2 plus, this is 9, 3 to the power of 2. For beryllium 3 plus, this is going to be 16, 4 to the power of 2. For boron 4 plus, Z is 5. Z squared is 25. So now you can see in helium plus, the energy of the electron is more negative than the electron in the hydrogen atom. How much more negative? 4 times more negative. Lithium 2 plus, 9 times more negative. Now the Redberg equation, in a hydrogen atom, when electron jumps from a higher energy level to a lower energy level, we can calculate the energy of these two levels using this -1 over 2n squared. Again, the unit is 4.36 attojoule. The energy of the emitted photon in this transition is simply the difference between the two energy levels. Higher energy level, lower energy level. The higher energy level is less negative. The lower energy level is more negative. This is the energy of the photon. And then we can calculate the wave number of the photon, which is 1 over lambda. The reciprocal of the wave number is the wavelength. The physical meaning of the wave number is the number of waves within 1 unit of length. So let's see. We're plugging h, the Planck constant, c, the speed of light. We plug in this one atomic unit is 4.36 attojoule. We get this equation. The wave number of the photon is equal to 1.097 times 10 to the power of 7 per meter. So this means roughly 10 million waves within 1 meter of length. And then times 1 over n1 squared minus 1 over n2 squared. n1 is less than n2. Therefore, this part is positive. You'll get a positive wave number and wavelength. This equation is the Redberg equation. Now let's look at the Bomberman series of the hydrogen atom. The Bomberman series consists of 4 visible spectral lines. They correspond to 3 to 2 transition, 4 to 2, 5 to 2, and 6 to 2. Can the electron jump from level 7 to level 2? Yes, but we will not be able to see it. It's in the near UV range. So now let's look at the equation. This is the Redberg equation, and I'm assuming N1 is 2 in the Bomberman series. And then we can just plug in numbers 3, 4, 5, 6 into this N2. And then we'll be able to calculate the wave number and, of course, the wavelength. The wavelength is simply the reciprocal of the wave number. So let's look at this Wolfram Alpha website. I used this website to do the calculation. So over here, this part is the wave number. 1 over the wave number is the wavelength. So the wave number is the Redberg constant, 1.097. And over here, I'm using E7 as 10 to the power of 7 times 1 over 2 squared minus 1 over 3 squared. So you can see the result is given here, 6.56 times 10 to the power of negative 7 in meters. This is because I used the SI units in the calculation. And we can convert this to nanometers. It's just 656 nanometers. So that's why we have this number here. You can plug in number 4, 5, 6 and get the 3 other spectral lines. Again, these 4 spectral lines are within the visible range. I think the visible range is roughly between 400 nanometers to 750 nanometers. Now let's look at the color of these 4 visible lines in the Bomberman series. 600 something, that's the red, and we have a green, and we have 2 blues. This is more like violet. This is the Bomberman series. Okay. There are other series. Lyman, that's in the UV range, and then 2 others are in the infrared range. So let's look at this Lyman. This is from 2 to 1, 3 to 1, 4 to 1, 5 to 1. So I think this one is the transition from 2 to 1, 3 to 1, 4 to 1, 5 to 1. 5 to 1 has a larger energy gap than the others, therefore shorter wavelengths. So we can click this as well, Wolfram Alpha. In here, I was calculating the first UV line in the Lyman series. So this is 1 over 1 squared minus 1 over 2 squared. The wavelength is 122 nanometers. Alright, so or 1.22 times 10 to the power of negative 7 meters. Alright, so 100 over here, 122 nanometers in the UV range. This is 3 to 1 transition with a shorter wavelength.